In this video, we begin chapter 10 of our text. In particular, we look at the Euler identity. And more specifically, in this video, we'll take a look at actually some geometry, and we'll see a connection to graph theory. So we begin with the 5 Platonic solids, or the 5 regular polyhedra. So a polyhedron is a three-dimensional object whose boundaries consist of polygonal plane surfaces. So we call these plane surfaces, so these are these things in each polyhedron. These are the faces of the polyhedron. The boundary of any two faces, the two-dimensional boundary is called an edge, and the one-dimensional boundary where two faces meet is called a vertex. So this is different from our notion of vertex in graph theory. Sorry, let me do V for vertex. We have vertices, edges, and faces when we're talking about polyhedra. So we usually let V for any polyhedra be the number of vertices. So this is where the faces meet at a zero-dimensional. Sorry, I think I said this bad earlier. The vertices are the zero-dimensional boundaries. Edges are the one-dimensional boundaries. We let E be the number of edges and F the number of faces. So here with the tetrahedron, I outlined the faces by actually drawing these edges. So these are the one-dimensional boundaries of the faces, and the vertices would be these zero-dimensional boundaries of the faces. And we can do this for each one of the regular polyhedra. And one thing in this video I want to do is keep track of the number of vertices, edges, and faces of each of the polyhedra. This will give rise to what's called the Euler's Polyhedra Formula, or Euler's identity polyhedra. So, what I do want to make clear here is the connection back to graph theory. So take any one of these regular polyhedra, and one way you can sort of visualize this is if you put a light above one of the faces of the tetrahedron, or any of the regular polyhedra. You put a light above the tetrahedron, and imagine this is not a solid figure, but more like a wireframe, where the edges are, I don't know, made out of aluminum, something like this. And so you can see through the faces. If you shine a light along one of the faces, maybe say here, oops, it's black, here, and you shine a light, what would be projected over here on the side would give rise to a graph. So I'll sort of show how this works. When the light shines, this first face will end up being the outer boundary of the graph. And here, the vertices of the polyhedron turn into vertices of the graph. So notice this has 4 vertices, and we should see 4 vertices in the graph. So notice the tetrahedron, each face is triangular, has 3 sides to it, and we see in the graph each face, or what we'll call regions of the graph, is a 3-cycle, is a triangle in the graph theoretic sense. So the tetrahedron gives us this graph, and this we can actually recognize as K4. Right? This is actually K4. The octahedron, again, we do the same thing. We place a light and then shine it. Again, look at the faces of the octahedron. The faces of the octahedron are triangular, and so again, we should see triangular. When I shine it across this first face, the outer boundary should be a triangle. So again, I'll see that outer triangle. And then you do have to do some visualizing here, but I'll draw it to see it better. What we'll get is another triangle face in the middle, and then these triangular faces connecting it. So now every region in the graph is defined by a 3-cycle or a triangle, including the outer region, the big triangle on the outside of this graph. So this is the octahedron. This actually ends up being, this is a graph we've seen a few times in recent chapters. This is K222, complete tripartite graph. The cube, again, we can do the same thing. This outer face will end up being this outer 4 cycle. Notice now each of our faces is a 4 cycle, and then this inner face will be a 4 cycle here. And the boundary of any one of these regions in the graph is a 4 cycle, including the outer region. So maybe one thing I'll make clear here, I want to count the number of regions or faces. So there's one region here, one region here, one region here for the tetrahedron, but we also have an outer region. So maybe I'll call this like R1, R2, R3, and R4 is the outer region. So each of the faces of the tetrahedron corresponds to a region in the plane that's divided up by the edges and vertices of the graph. So there are, so here V, our number of vertices, is 4. The number of edges in either the graph or the polyhedron is 6. And then the number of faces of the polyhedron, also the number of regions in the graph, is 4. So that was the tetrahedron. For the octahedron, well, how many vertices do we have? We have 6 vertices. How many edges? Well, it's K 2, 2, 2. So we should have 8 edges. No, sorry, not 8 edges. We should have 12 edges. Right, every vertex has degree 4. And number of faces, same as number of regions, right? We'd have 1, 2, 3, 4, 5, 6, 7, 8. 8 faces or regions, octa 8. And then we have the cube. So let's see, vertices here. We have now 8 vertices. How many edges? We have 12 edges. And finally, how many faces or regions? Well, we have 1, 2, 3, 4, 5, and finally 6, the outside region. Right, the outside region, this is why we're counting this, because this corresponds to a face on the cube. In particular, this front face is the outside region. Okay. So let's move on. These were the easier ones. These ones I'm not going to draw for you. I'm just going to give you the graph that corresponds to it. It would take a little bit too long to draw. But the icosahedron, how many vertices does the icosahedron have? We can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Icosahedron has 12 vertices. It has, well, each vertex has 5, degree 5, and you can see that on the polyhedron, the icosahedron, there are 5 faces at every vertex. Each face is a triangle, and they all meet at 5, and so 5 times 12, 60 over 3, or over 2 is 30. There's 30 edges here, and number of faces, well, there's 20, Greek ikosa, or ikos. And then we have the dodecahedron. The dodecahedron, each vertex here, there's 1, 2, 3 faces that meet at each vertex. And how many vertices do we have? 1, 2, 3, 4, 5. You might actually remember this one from the Icosian game of Hamilton. There are 20 vertices in the dodecahedron. Each one has degree 3, so there are 30 edges. And how many faces? There are 12 faces for dodeca. Notice how here the icosahedron and the dodecahedron, the vertices and the faces switch with each other. These are known as duals of each other. That was the same for the cube and the octahedron were also duals of each other. Okay, so, right. We're getting to keeping track of these vertices, edges, and faces. I guess let me just write these down one more time. So the tetrahedron was 4, 4. Cube was 8, 12, 6. Octahedron, right, is the dual of the cube. It's 6, 12, 8. Notice how the vertices and faces switch. Dodecahedron was 20, 30, 12, and then 12, 30, 20 for the icosahedron. And the thing to notice here, and it might be kind of surprising that it was Euler that was the first mathematician to observe the following fact about these polyhedron, and these are the regular polyhedra, but this also works for any polyhedra, that the following identity holds. So this is the Euler polyhedral formula. Even though it's not really a formula, it's an identity. V, the number of vertices, minus the number of edges, plus the number of faces, is equal to 2. So one of our first goals is going to be, by the way, he took Euler, the first time he noticed this, he didn't have a proof of this formula. In his second paper, he attempted to prove it, but there were some missteps in it. It wasn't generally accepted as a valid proof. It was finally proved by Legendre, French mathematician later on. But we're going to prove actually a more general formula than this. We're going to prove the graph theoretic formulation of this, which will be for all planar graphs, a special kind of graph that will imply this result. And our proof isn't going to be so difficult. So we'll introduce planar graphs in the next video as a quick sort of foreshadow to that. Notice that each one of these graphs that I got from the polyhedra, I could draw them with no two edges crossing. So not every graph has this property, right? Not every graph has this property that I can draw it with no edges crossing. But any graph I get from one of these polyhedra has that property. They're all what are called planar graphs. We'll talk more about that in the next video. I'll see you there.